When evaluating some of these flux integrals, the integrals can get kind of tedious to evaluate. We're now going to talk about a theorem that lets us skate by some of this with a lot less trouble than we had before. And this is the divergence theorem. And what this does is it allows us to replace a flux integral with a triple integral. So what this says is that if we've got the flux through the surface S, and if S is a closed surface. Now, closed means there's no hole in it. I can't get from the inside to the outside. We'll see some examples of surfaces that are closed and that are not closed. But if S is a closed surface, then the flux through the surface, given the vector field F, is equal to the triple integral over a certain region of the divergence of F dV, where the boundary of the region is S. Let's look at an example of what this means. Say we're looking at the flux given by the field F, where F is x plus e to the y squared, x minus z to the z, and then x squared plus y to the e to the x minus 2z. Say we have this vector field right here, and we want to apply, and this is over, S is the unit sphere. Well, first off, the unit sphere, this is closed. It's closed because if you take any point inside the unit sphere, the only way to get out of the sphere is to actually cross over the boundary in the first place. So this is a closed surface. If we only had the top half of the sphere, that would be open, because you can get from the inside to the outside by sort of crawling through the bottom. But this is a closed surface, so we can apply the divergence theorem on this. And this turns into the triple integral over the unit ball, that is the sphere filled in, of the divergence of F dV. So this gives us the triple integral over the ball. Now the divergence means take the partial of F1 with respect to x plus the partial of F2 with respect to y plus the partial of F3 with respect to z, where the F1, F2, and F3 are the three components of our field in the first place. So we go and simplify these. The partial of F1 with respect to x, here's F1. We take its partial with respect to x, we get 1. The partial of F2 with respect to y, well, this is F2. It doesn't depend on y, so that partial is 0. And then the partial of F3 with respect to z is negative 2. So all of those ugly components just dropped right out because the various components didn't depend on those extra independent variables. So this, we can simplify this to give us the triple integral over the ball of negative 1 dV. This negative 1 is constant, so we can pull it right out of the integral. Negative 1 triple integral of dV. This, by definition, is the volume of the ball. So it's negative 1 times 4/3 pi times the radius cubed. So that just gives us negative 4/3 pi. Now if we had tried doing this by a straight up flux integral, we may not even be able to make any headway, because some of these don't have elementary antiderivatives, so it might have been impossible to do without divergence theorem. Now the divergence theorem you can apply on surfaces that aren't closed, but we've got to do a little bit of extra work. Let's say we were looking at the flux through the surface S, where S is the part of z equals 5 minus x squared plus 2x minus y squared above the xy plane. So above z equals 0. Now to get an idea of what this thing is, it may be handy to complete the square. Right, so if we take this, if we look at just those x's, factor out that leading minus sign, we've got x squared minus 2x minus y squared plus 5. We take half the middle term here is negative 1. We square it is positive 1. And we just added negative 1 here, so we'll go and add positive 1 to make up for it. So this gives us z is negative x minus 1 squared minus y squared plus 6. So this is actually a paraboloid. So we want the part of the paraboloid that's above the xy plane. So just making a rough sketch of this, our x, y, and z. The vertex of this paraboloid should be at x equals 1, y equals 0. So it's right above here. We've got the vertex of our paraboloid, and it opens downward. And we see it's going to cross the xy plane in a circle. So our surface is just the part of this paraboloid that's above the xy plane. Now this surface is not closed, because if you took a point inside that paraboloid, you can get out of it by moving downward, and then you're outside, because this surface does not include the bottom. So that means we can't apply the divergence theorem as is, but we could extend the surface a little bit. Let's take a new surface. Let's take S prime to be the original surface plus that cap, the disk that's along the bottom of the surface. So we take the original surface and add on the cap, then the surface is closed. So we're going to close it off, and then we can apply the divergence theorem on this new surface. So if we look at the flux through the new surface, f dot ds, this is now equal to the triple integral over that solid region of the divergence of f dv. And then what we could do here is break this into two pieces, two separate integrals, one for the surface and then one for the disk, and then solve for the one that's missing. Let's do a specific example on this with this region. Let's take a specific vector field. Let's do this with f equals x plus y, y plus z, x plus z. Let's take that as our field, and we'll do the integral over, we'll do the flux through just that top surface, just the paraboloid. So if we look at what we've got set up so far, we've got that the double integral over the paraboloid, the flux through the paraboloid, plus the flux through the disk is going to equal the divergence of f through the entire solid region, that bullet-shaped region. So let's go through the pieces of this that are not going to be too bad. The paraboloid is going to be the worst of the three, but that's the one that we want to get in the end. So let's look at the disk first. If you look at the flux through the disk, well, first the disk is given by that's the floor of this region in here, and that's given by the plane z equals 0. That's the xy plane. So that disk is the equation z equals 0. So to get our ds, we're going to take our two tangent vectors and cross them. dA. So if we were to parameterize this disk, the disk z equals 0, so x and y are both free. So if we were going to parameterize this out, we could say x is t, y is s, z is stuck at 0. So then t1, that'll be the partial of our parameterization with respect to t. So that's 1, 0, 0. If we look at our second tangent vector, we take the partials with respect to s, and we've got 0, 1, 0. And if we cross those two, our ds, well, this is just I, and this is j. If we cross those two, I cross j gives us k. We've just got to make sure we have the right orientation. Remember, when we do these flux integrals, we're always looking for the normal vector that's pointing outward. So let's just go and take a look at this picture. K, the k vector is pointing upward along the z-axis. We want the one that's pointing downward. That just says that we cross these in the wrong order. So our ds here should be negative k dA. Okay, so to finish up this disk part right here, if we want to get our limits of integration, and we have a disk, so getting the limits, we're probably going to need to go to polar. So if we look at this, this double integral here is the double integral over the disk of f dot ds. Now our f was given by this expression right here. Let's expand that out using our parameterization. X is t, y is s, y is s, z is 0, and then x is t, z is 0. And we're dotting this with ds, which is 0, 0, minus 1 dA. So this gives us the double integral over the disk. We expand this dot product out. The x components cancel, they zero out, the y components zero out, and we're left with just negative t dA. Okay, now we've got to change this to polar because we're integrating over a disk. And if we look at what our, so if we change this to polar, we've got t equals r cosine theta. We have s is r sine theta. And our limits of integration, we've got a full disk of radius 1. So our limits of integration will be 0 to 2 pi and 0 to the radius of the disk. And then we have minus r cosine theta times the Jacobian times dr d theta. And we can use the Box theorem on this to expand this out, 0 to 2 pi of cosine theta d theta times the integral from 0 to 1 of minus r squared dr. And this first integral zeroes out. So this whole thing is 0. So this entire disk flux is 0. Okay, so let's just update what we've got so far. If we just copy down the equation that we've got, this says that the double integral over our surface, this flux through the paraboloid of f dot ds is equal to the integral of the divergence of f dv over the whole solid region. Okay, so we've managed to get one of the pieces out of the picture. This thing is zeroed out. And if this hadn't been 0, if we would get a number for this, we would just move the number over to the other side because we want to solve for the flux that we're looking for in the first place. So now this divergence here, if we go and expand this divergence out, it's a triple integral of the region of the divergence of f. So our f was given up here. If we take the divergence, we take the partial with respect to x here is 1. The partial with respect to y is 1. The partial with respect to z is 1. So the divergence is just 3. This gives us 3 dv. Okay, that 3 can come out of the integral. So this is 3 times our triple integral dv over that region. And now we've got to get our limits of integration on that region. So if we go back and look at our original picture, if we look at this disk here, this disk, we'd like to go to polar, but it's got the wrong center. So we're going to need to recenter that circle. So as it stands, if we looked at z equals 0 gives us the formula for our disk. If we take this equation we have for z so far and we shuffle some things around, we've got x minus 1 squared plus y squared equals 6. Now this is almost a circle of radius square root of 6, but the problem is it's been shifted around. So let's do a change of variables on this to switch this up. If we let u equal x minus 1 and v equal y, then this becomes u squared plus v squared equals 6. So now it's got the right center and we can change it to polar. And the Jacobian of this transformation, this uv transformation, is 1. We can go and verify that by taking our partial derivatives. So we got the Jacobian of this transformation is 1. If we go back and look at what we've got here, our outer two variables right here, we're going to go to polar. So the theta goes from 0 to 2 pi, the r from 0 to square root of 6 because that's the radius of a circle, and then our z's go from the bottom surface, which in this paraboloid shape here, the bottom surface was z equals 0, to the top surface, and the top surface was given by that paraboloid, which we have this formula for right here. This is 6 minus x minus 1 squared minus y squared. But we changed that, since we switched over to u and v, we have that as 6 minus u squared minus v squared. So this is 6 minus u squared minus v squared, but we changed this to polar. So that's 6 minus r squared. Then we've got our Jacobian. Now we have the Jacobian from converting to u and v, which was 1. Then we need another change of variables when we switched over to polar, which introduces that Jacobian, which is r. Then we've got dz, dr, d theta. And now we're ready to evaluate this. So this gives us 3, integral from 0 to 2 pi, integral from 0 to radical 6. Now our innermost integral, this is with respect to z, and 1r is constant, so we get rz, evaluated from z equals 0 to z equals 6 minus r squared, dr, d theta. So we've got 3, integral from 0 to 2 pi, integral from 0 to radical 6. If we now plug these limits in, we've got 6r minus r cubed, dr, d theta. We can now integrate this term by term. We've got 3 integral from 0 to 2 pi, and then 3r squared minus r to the 4th over 4, evaluated from r equals 0 to r equals radical 6. Now at r equals 0, everything zeroes out. And at radical 6, well, this is radical 6 squared is 6, times 3 is 18. Then over here we have radical 6 to the 4th. We simplify some of our radicals. That gives us 6 squared, which is 36, divided by 4 is 9. And then this is with respect to theta. We subtract those out. That's going to give us 9, which will come right out of the integral. So we've got 27 integral from 0 to 2 pi d theta. And this integral just gives us 2 pi. So this, we multiply these out. We've got 54 pi. So that 54 pi was the triple integral. So this right here was 54 pi, which means the flux through our surface is also 54 pi. So this is an example of using the divergence theorem. When the surface isn't closed, we've got to do a little bit more work, but at least it saved us from having to do the flux through that bizarre surface.